Welcome to this problem walkthrough. Today, we'll explore the problem longest chunked palindrome decomposition. This is a fascinating string-based challenge that tests your understanding of palindromic structures and recursive problem solving. Let's dive in and break down the solution step by step. In this problem, you're given a string called text, and your goal is to split it into the maximum number of substrings that satisfy specific conditions. First, every substring must be a non-empty palindrome. Second, when all these substrings are concatenated together, the result must equal the original string text. Finally, you want to maximize the number of substrings in your decomposition. A palindrome, as a reminder, is a string that reads the same forward and backward. For example, radar and level are palindromes. The input is a single string made up of lowercase English letters, and the output is an integer representing the maximum possible number of palindromic substrings. This gives you a clear goal: find the optimal way to split the string while following these rules. To understand the problem better, let's look at an example. Suppose the input string is text equals gyubtif hello Adam hello uptifki. The output for this input is 7. Here's why: the string can be split into 7 palindromic substrings. These are GHI, ABCDF, hello, Adam, hello, ABCDF, and GHI. Notice that each of these substrings reads the same backward as forward. Furthermore, when you combine them, the result matches the original string. This example demonstrates how the problem leverages the symmetry of palindromes to maximize the number of valid splits. Now, consider another example with the input text equals merchant. The output in this case is 1. Why? The string merchant itself is not a palindrome, and there are no valid ways to split it into smaller palindromic substrings. As a result, the only option is to treat the entire string as a single substring, meaning the maximum number of substrings is just 1. This shows that not every string can be split into multiple palindromic parts. Here's one more example to illustrate the problem. If the input is text equals Ababa, the output is 4. The string can be split into the following palindromic substrings: AAA, BB, and AAA. Each of these reads the same backward as forward, and when combined, they recreate the original string. So, the maximum number of substrings here is 4. This example highlights how identifying smaller palindromic segments within the string is key to maximizing the result. Finally, let's consider some constraints and edge cases. The length of the string text can be as small as 1 or as large as 1000, meaning your solution must be efficient enough to handle very long strings. The string consists only of lowercase English letters, so you don't need to worry about special characters or spaces. For edge cases, if the string is already a palindrome, the answer is 1 because no further splits are possible. Similarly, for a single character string like a, the answer is also 1. If the string contains repeated characters, like AAAA, the output will depend on how many valid palindromic splits can be formed. These constraints and edge cases are crucial to consider as you work toward an optimal solution. Let's start by considering the brute force approach to solving this problem. The idea here is to examine every possible way to split the string into 2 halves and check if the resulting substrings satisfy the palindrome condition. Specifically, we take the first chunk starting from the beginning of the string and compare it to the last chunk starting from the end. If those 2 chunks match, we count it as a valid chunk and then recursively apply the same process to the middle portion of the string. While this approach does work, the key issue is its inefficiency. Since we need to explore all possible partitions of the string and compare the chunks, the time complexity becomes quadratic or worse, depending on how the implementation is structured. This makes the brute force method impractical for larger strings, where the number of substrings to check grows significantly. Now, let's shift to an optimized approach based on a greedy strategy using 2 pointers. The main insight here is that we don't need to explore all possible partitions to find valid chunks. Instead, we can focus on the symmetry of palindromes by comparing prefixes and suffixes. Using this method, we use 2 pointers, one starting at the beginning of the string and the other at the end. We compare the substring formed by the left pointer with the substring formed by the right pointer. If they match, we count this as a valid chunk and move the pointers inward to analyze the next portion of the string. This process continues until the pointers meet in the middle. Any leftover portion in the center, if it exists, is counted as a single chunk. By processing each character only once, this approach achieves linear time complexity, making it highly efficient for long strings. Another approach to solving this problem involves dynamic programming, or DP, which focuses on avoiding redundant computations by leveraging memoization. The idea is to track the maximum number of chunks that can be formed for any substring of the input. To do this, we define a DP table where DP, I, J, represents the maximum number of chunks for the substring text, i.e. J. For each substring, we compare its possible prefixes and suffixes. If a match is found, we compute the number of chunks recursively and update the DP table with the maximum value. While this reduces redundant computations compared to the brute force method, updating and maintaining the DP table introduces additional overhead. The time complexity is quadratic, O(n squared), and the memory usage can also become substantial for larger inputs, making this approach less efficient than the greedy method. Given these considerations, the chosen strategy for this problem is the greedy two-pointer approach. It stands out for its efficiency, achieving a linear time complexity of O(n), which makes it particularly well suited for long strings. The implementation is also straightforward, relying on just 2 pointers and simple comparisons, which minimizes complexity. This approach leverages the inherent structure of palindromes by identifying symmetric prefixes and suffixes, allowing us to maximize chunks without performing unnecessary computations. Additionally, once a valid chunk is identified, it can be independently counted, and the problem is reduced to the middle portion of the string. While the dynamic programming method is valid, it introduces unnecessary overhead for this specific problem, as we don't need to store intermediate results. The greedy strategy strikes the perfect balance between simplicity and performance. Finally, let's discuss the trade-offs between the different approaches. The greedy two-pointer strategy is faster and more memory efficient than the dynamic programming approach, though it lacks the flexibility of DP when dealing with problems that have additional constraints. Compared to the brute force method, the greedy approach is drastically more practical, avoiding the prohibitive computational costs of exploring all partitions. By focusing on the symmetry of palindromes and leveraging the greedy strategy, we achieve an optimal solution that balances simplicity and performance. This makes it the best choice for efficiently solving the problem within the given constraints. To tackle this problem, we start by understanding the brute force approach. The goal is to determine if a string can be split into 2 substrings, both of which are palindromes. A string is a palindrome if it reads identically forward and backward. The brute force method involves iterating through every possible position in the string to create 2 substrings. For each split, we check if the left substring and the right substring are palindromes. This is done by comparing each substring to its reverse. If we find at least one split where both substrings are palindromes, we return true. Otherwise, after exhausting all possible splits, we return false. This approach ensures we evaluate all potential splits in a thorough, systematic way, but as we'll see, it has its limitations in terms of efficiency. The brute force approach requires several key operations. First, splitting the string at each index involves slicing, which takes time proportional to the length of the substring. Second, checking whether a substring is a palindrome involves comparing the string to its reverse, which also takes time proportional to the substring's length. Since we repeat these steps for every possible split, the time complexity adds up. For a string of length n, there are n1 possible splits. For each split, the palindrome check can take up to O(n) time in the worst case. This results in an overall time complexity of O(n squared) for the brute force method. While this is manageable for smaller inputs, it can become inefficient for longer strings, making it necessary to explore optimizations. To optimize, we can avoid redundant computations by pre-computing palindromic substrings. Using a dynamic programming approach, we can build a 2D Boolean array called isPalindrome. This array stores whether any substring of the string is a palindrome. The base case is simple: single-character substrings are always palindromes. For 2-character substrings, we check if both characters are the same. For longer substrings, a substring is a palindrome if its first and last characters match and the substring between them is also a palindrome, which we can determine using the pre-computed table. Once the isPalindrome table is constructed, we can check all potential split indices. For each split, we simply look up whether the left and right substrings are palindromes using the pre-computed information. This avoids repeatedly recalculating the same results, making the process significantly more efficient. After pre-computing the palindrome information, we proceed to check all possible splits using our isPalindrome table. For each split index, we check whether the left substring, defined by isPalindrome 0, I1, and the right substring, defined by isPalindrome I, N1, are both palindromes. If we find a valid split where both conditions are true, we return true immediately. If no valid split is found after examining all possibilities, we return false. The pre-computation of the isPalindrome table takes O(n) squared time, and checking all splits takes O(n), leading to a total time complexity of O(n) squared. While the overall complexity remains the same as the brute force method, the optimization eliminates redundant palindrome checks, making the process faster in practice. The key insights behind this optimized approach are rooted in avoiding redundant computations and leveraging dynamic programming. By pre-computing palindrome information, we ensure that each substring is checked for palindromicity only once, significantly reducing repetitive work. The isPalindrome table takes advantage of overlapping subproblems, where knowing the status of smaller substrings helps determine the status of larger ones. It's also important to consider edge cases. For instance, strings of length 1 will always return false because no valid split is possible. Strings where all characters are identical can be split at any position to produce valid palindromes. On the other hand, strings with no palindromic substrings will always return false. These insights ensure our algorithm is both efficient and robust across a variety of inputs. This solution implements the longest chunked palindrome decomposition problem using a greedy two-pointer approach. The function longest decomposition takes a string text and determines the maximum number of palindromic chunks the string can be split into. We initialize two pointers, left and right, to traverse the string from the beginning and the end, respectively. The variable count keeps track of the number of palindromic chunks found. We also maintain two temporary strings, temp_left and temp_right, to build potential substrings from the left and right sides of the string. In each iteration, we add the current characters from the left and right pointers to temp_left and temp_right. If temp_left matches temp_right, it indicates that we have found a palindromic chunk. We then increment the count and reset both temp_left and temp_right to empty strings for the next potential chunk. The process continues until the left pointer surpasses the right pointer, ensuring that all characters are processed. Finally, the function returns the total count of palindromic chunks. This approach ensures efficiency by leveraging the two-pointer technique and avoids unnecessary computations. It handles edge cases like single-character strings and strings that cannot be split into smaller palindromic chunks gracefully, as the algorithm inherently accounts for these scenarios during the traversal. This is the Java implementation for LeetCode problem number 1147, longest chunked palindrome decomposition. The logic mirrors the provided Python solution, using two pointers and string builders to construct chunks from both ends of the string. Key differences include the use of string builder for efficient string manipulation and Java-specific syntax such as explicit type declarations. The solution splits the string into the maximum number of palindromic chunks by comparing the left and right substrings as they are built. To solve the problem of finding the longest chunked palindrome decomposition, we start by initializing our pointers and temporary variables. Here, left and right are set to the beginning and end of the string respectively, while count is initialized to 0 to keep track of the number of chunks. Temp_left and temp_right are empty strings that will help us build potential palindrome chunks from the left and right sides. In the first iteration, we add the character at text, left, which is G, to temp_left, and the character at text, right, which is I, to temp_right. Since these two temporary strings are not equal, we update the pointers by incrementing left and decrementing right. In the second iteration, we add the next characters, H and H, to temp_left and temp_right, but the strings still do not match. We continue moving the pointers inward while building these temporary strings. In the third iteration, temp_left becomes GHI and temp_right also becomes GFI. Now that the two strings match, we have identified a valid palindrome chunk. We increment count by 1, reset both temp_left and temp_right to empty strings, and continue processing the remaining part of the string by advancing the pointers. This process repeats as we identify additional chunks such as ABC, def, hello, atom, and another hello. Each time we find matching chunks, we increment the count and reset the temporary strings to prepare for the next chunk. Once all chunks have been processed, the final value of count, which is 7, is returned as the total number of palindrome chunks. Now, let's look at a second example where the input string is antepresitepsiprenta. We start with the same initialization as before, setting left to 0, right to 20, and initializing count, temp_left, and temp_right. The first chunk we identify is anta from both ends of the string. Since temp_left matches temp_right, we increment count to 1 and reset the temporary strings. Next, we identify the chunk presa from both sides, which also match, so count is increment to 2. Finally, we find teps in the middle, which again matches on both ends. By repeating this process through the entire string, we determine that the total number of palindrome chunks is 11. This is returned as the result. For our third example, we have a much shorter input string, AAA. Starting with the same initialization, we set left to 0, right to 2, and initialize count, temp_left, and temp_right. In the first iteration, we add the character from both ends of the string to temp_left and temp_right. Since these two strings are equal, we increment count to 1, reset the temporary strings, and move the pointers inward. Now, left and right both point to the middle character. In the second iteration, we repeat the same process, adding it to both temp_left and temp_right, and again finding a match. We increment count to 2 and prepare for the next step. Finally, the middle character itself is treated as its own individual chunk since it cannot be paired with any other character. This is an important aspect of the algorithm to ensure that every part of the string is accounted for. We increment count 1 last time, bringing the total to 3. This value is returned as the result, representing the total number of palindrome chunks in the string. To analyze the time complexity of this algorithm, we start by noting that it processes the input string text by iterating from both ends toward the center. If the length of the string is n, the while loop ensures every character is considered exactly once, resulting in at most n iterations. Within each iteration, two key operations occur. First, characters are appended to temp_left and prepended to temp_right. These operations are constant time, or O1, in Python. Second, the algorithm checks if temp_left is equal to temp_right. This equality check involves comparing slices of the string, and in the worst case, the length of these slices can grow to k, where k is the current size of temp_left or temp_right. If no chunks are found, k can grow to half the string length, or n/2. Combining these, the loop runs n times, and each comparison in the worst case takes O, k, leading to a total time complexity of O, n*k, or O, n*n/2, which simplifies to O, n squared. Now, let's consider the best case for time complexity. In scenarios where the string can be easily chunked, such as with repeated patterns like appcap, temp_left and temp_right are reset frequently, keeping their sizes small. Since k remains constant in these cases, each equality check takes O1. With the while loop still iterating at most n times, the total time complexity simplifies to O(n). Summarizing the overall time complexity, the worst case remains O(n squared), while the best case achieves an optimal O(n). Shifting to space complexity, the main contributors are temp_left and temp_right, which store chunks of the string. In the worst case, their sizes can grow to n/2, leading to O(n) space usage. Other variables, such as left, right, and count, only require constant space, or O(1). Therefore, the overall space complexity is dominated by temp_left and temp_right, resulting in O(n). When comparing this algorithm to a brute force approach, the efficiency gains are clear. A naive solution would involve generating all possible substrings and checking each for palindromic properties, leading to a time complexity of O(n cubed). In contrast, this algorithm employs a greedy approach, avoiding substring generation and directly comparing chunks, which reduces the worst-case complexity to O(n squared). For strings that can be chunked into smaller palindromic parts, the best case reaches O(n), making this method highly efficient under favorable conditions. From a mathematical perspective, the dominant contributor to time complexity is the equality check within the while loop, which scales with the size of temp_left or temp_right. In the worst case, these chunks grow to n/2, resulting in quadratic behavior. However, for strings with frequent resets due to easy chunking, these comparisons remain constant, yielding linear complexity. Overall, this algorithm offers a balanced trade-off between efficiency and simplicity, significantly outperforming brute force while maintaining a straightforward implementation. When tackling problems like longest chunked palindrome decomposition, there are several common mistakes to watch out for. First, ignoring edge cases can lead to runtime errors or incorrect results. For instance, scenarios involving empty strings, single characters, or maximum constraints often reveal gaps in the code that standard test cases might miss. Always ensure your solution handles these edge cases explicitly. Next is relying on inefficient brute force solutions. While they might work for small inputs, they can result in timeouts on larger datasets. For example, using an O(n)² approach when the problem can be solved in O(n log n) is a missed opportunity for optimization. Overcomplicating the solution is another frequent pitfall. Adding unnecessary logic not only makes the code harder to debug but also increases the chances of introducing bugs. Simplicity and clarity should always be prioritized. Additionally, incorrect handling of indices is a common challenge in string and array problems. Off-by-one errors or mismatched start and end indices can cause subtle bugs, so always double-check your boundary conditions. Finally, overlooking space complexity can be an issue. Even if your solution runs within time limits, excessive memory usage, especially with recursion or auxiliary data structures, can lead to crashes. Being mindful of both time and space constraints is key to robust problem solving. Now let's focus on some interview-specific insights that can help you stand out. Paying close attention to constraints is crucial. Constraints like n equals 10 to the power of 5 often hint at the expected time complexity, guiding you toward more efficient solutions such as O(n) or O(n log n). During interviews, it's also important to communicate your thought process clearly. Explaining your approach aloud not only helps the interviewer follow your reasoning, but also allows you to earn partial credit even if your solution isn't perfect. Start with a brute force approach to demonstrate a basic understanding, and then iterate to refine and optimize it. This process shows your ability to balance trade-offs between time and space complexity. Recognizing common problem patterns is another valuable skill. For example, techniques like sliding windows, dynamic programming, binary search, or graph traversal often apply to a broad range of problems. Spotting these patterns early can save significant time and effort. Additionally, exploring related problems can deepen your understanding. For instance, problems like palindrome partitioning, longest palindromic substring, valid palindrome, and partition labels are all closely connected to the techniques used for this problem. Reviewing these can help reinforce key concepts and prepare you for variations. Finally, let's explore some alternative approaches that can be effective for problems like this. Dynamic programming is especially useful when you encounter overlapping subproblems. By breaking the problem into smaller, manageable pieces and storing intermediate results, you can often achieve significant performance improvements over recursive backtracking. The two-pointer technique is another powerful tool, particularly for string and array problems. By using two indices to traverse the data, you can often reduce complexity from O(n)² to O(n), making this approach both efficient and elegant. Greedy algorithms are worth considering when local optimizations naturally lead to a global solution. These approaches are often simpler to implement and can perform well for certain types of problems. Lastly, pre-processing can be a game-changer for problems with repeated queries. Techniques like prefix sums for range queries allow you to compute results efficiently, trading off a bit of upfront computation for faster query resolution. By leveraging these strategies, you can expand your toolkit and tackle a wider variety of challenges more effectively. Great job! We've now solved the longest chunked palindrome decomposition problem. Remember the importance of recursion and recognizing patterns in strings to simplify complex problems. Keep practicing, and I'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!